Okay, let's get class started. First off, there's a couple of homeworks due. One on a paper with a unique printing process that you choose, something you're interested in. So hopefully you have a good start on that. And if you're unsure as to how to find a good paper, I'd be happy to talk about that anytime. And then the second assignment you should be thinking about is related to your final paper and project. What are you interested in? How can you use some knowledge gained in this class around additive and polymers and composite materials, how it might relate to your research or what you want to learn in the future. And so I've chatted with a couple of you on topics. And really all this assignment is just a couple sentences on what your topic's going to be. And it's especially important that you see if you can find a couple references in the literature to help you. So oftentimes you have an idea. You need to look in the literature to see what other people have said about it. Is there enough information in the literature that you can write a viable paper on it? And so this is just starting to do some of the thinking now rather than trying to figure out a topic in December. Of course, you're allowed to change topics or tweak them however you want. The papers don't need to be on polymer chemistry or super detailed polymer science, but they should relate in some ways to a polymer and additive manufacturing. And the most important part of the paper is that it should be useful for you, either stuff you want to learn now for your current thesis projects or your current research, or things that might be useful in the future to you. So just do some thinking on that, and I'd be happy to Zoom or email about different ideas. So make sure that that stays on your radar screen. And over the course of the next month and a half, you should be working on this stuff to make sure you can get it in by finals week. Any questions or comments, anything people want to bring up? Okay, so these slides are on the box. We're on lecture 9. And the lectures are just numbered in some kind of numerical order. But I had a question about cyclic thermal stress on email that we were talking about. And I thought that I would go into a little bit more detail because cyclic thermal stresses are really important, especially when we're thermally processing polymers. So we're going to take a little bit of a round trip back to FDM or material extrusion AM and selective layer sintering of polymers. And so cyclic thermal stresses don't really occur in what we've talked about recently in terms of material jetting or stereolithography. There's other types of defects, which we'll talk about either later on this lecture or next time. But I figured it was worthwhile to have a discussion on thermal stresses, how they show up in 3D printed parts, and what research people have done on thermal stresses, because this is what causes some of the defects in 3D printed parts. So you can take this as a little bit of a reminder that thermal processing is still important in polymers. And we'll go back and forth in the second part of the semester between a few different 3D printing technologies now that we have a lot of things under our belt. So the first paper that I like in this area is referenced here. And so let me get my stylus. Is referenced here. And so I encourage you to check this out because they have a really nice experimental setup and they have a really nice way to explain what they're doing in terms of figuring out all the cyclic thermal stresses as they go and build materials. So this is they're basically making plates. And they have different thermocouples in different positions that are labeled. And so this gives all the dimensions of what they're interested in. So they're 3D printing basically over this plate. And what you see, so this is for thermocouple 3 and 3B. So if we go back, here's 3 and 3B. They were backups of each other. You can see that the temperature goes up and down depending on the passes that they make over the whole or near the hole. And so this starts to get really interesting because you have build time here in seconds. So this is over the course of about an hour or close to an hour. And you see departures between something that approximates the printing temperature, although it's not quite as high as the hot end temperature, and the baseline temperature or the build plate temperature down here. So now in this one location, in this 3D printed part, the temperature is going up and down over the course of an hour. And so a lot of you have some background in engineering, and you know, as you thermally cycle a part, you can get stresses built into the part from this thermal cycling, and also thermal cycling of one location in this plate that increases the volume of that material due to the coefficient of thermal expansion. And so you can get built-in stress by heating up one part of the plate and not the others. So this is really cool. We've seen a little bit of this before from previous papers, and we'll look at that again to remind you. But now when you start to put all this together, so you have all these thermocouples in all different locations, and you're doing printing at plus minus 45, you can see at the 7th layer, 8th layer, 9th layer, 13th layer printing, you still have significant departures of temperature compared to what the bulk temperature is. So this now gets really at the heart of the matter of really complicated cyclic thermal stresses in parts, and learning how to model this, or being able to model a whole part layup like this, is really difficult because you need to know all about the heat transfer, the heat conduction, coefficient of thermal expansions, all those sorts of things. And so we still don't have a comprehensive thermal model for a lot of this printing technology, although I'll show you an example of one in the future when we talk about a little bit about control software and how people are trying to control these printers. But this demonstration, and this is just a nice experimental paper because there's a lot of data in it. This is just a demonstration of how complicated it can get with these cyclic temperatures. And this is unlike all other sorts of polymer processing that we do. Usually you have polymer at room temperature, you heat it up, you form it, then you cool it down, and you have your finished part. Now, cyclic thermal stresses occur in use in, say, under hood automotive components where you're turning off and on the engine, or in hot, cold climates, say the difference between Phoenix, Arizona in the summertime versus Flagstaff, Arizona in the wintertime. You can imagine that there's a lot of cyclic thermal stress in extreme environments. Of course, space, this is really important because one side of the satellite is really hot and the other side is really cold as it faces away from the sun or towards the sun in space. And so we're used to analyzing components for cyclic thermal stress in use, but this is analyzing components for cyclic thermal stresses as they're being built, or as you're creating all these additive interfaces, because remember, this is material extrusion AM. So you're trying to make interfaces and do road adhesion in this cycling thermal environment. And that's hard. That leads to defects and failures, and we'll talk about that. But if you're interested in how complicated this gets, or if you're interested in setting up your own experiments along these lines, this is a cool paper to check out. So you can see the result of this warpage and shrinkage and thermal stresses just in simple demonstrations of material extrusion AM, say, in a desktop printer. And so this is from this is a picture from one of the online websites in terms of what failures are in material extrusion AM and how to fix it. And there's a lot of good know-how either in the community sites or in the manufacturer's websites. But this is a really interesting statement. If we could keep the whole 3D printed model at the exact same temperature all the time, we wouldn't get any warpage. But this is just really not possible. Even in industrial AM, where you have an oven or you have a thermal chamber, it's really hard to keep the part at a temperature near where you're extruding it, because of course you get slumping and other things like that. So there's always a temperature gradient. Ovens help with that, but this happens often, and so we need to figure out how to combat this sort of cyclic thermal stress. And so on a desktop printer, they said getting the material to hold on to the build surface is one part of it, because the build surface can constrain this warpage and deformation. And we'll talk about a couple of other failures here in material extrusion AM in a second. So people who do 3D printing have seen this. There's some strategies around this, and we'll talk about that. So there's some how-to guides, like I said. Here's one from Ultimaker on how to fix warping in terms of adjusting the build conditions, and I'll leave you to read that webpage if you're interested in it. Gives you some resources to think about. One cool idea is if you can't have an oven in terms of maintaining temperature across the entire build, printing this draft shield is in essence keep some of the heat inside the part. And so if you can prevent convection currents or air current drafts in your build plate, this is one way to help alleviate some of the warpage. Another really important way that warpage is alleviated in 3D printing polymers especially is to change the properties of the material. So in a lot of cases, so this is a pure polymer. I think it's nylon. We know that it's pure polymer because it's white, and so it's unfilled. It doesn't look like it's filled with silica or anything like that. And you can see when you print this long cantilever, you get this warpage right here. However, when you use something that's a stiffer material, so this is a filled nylon composite, and I think it has carbon fiber in it. Yes, Onyx is carbon fiber reinforced nylon. It's about 3.5 times stiffer than nylon. And a stiff material will often warp less than a material that's more flexible. So you have built-in stresses, and if the material is flexible, those built-in stresses, you can visualize them, the material will warp. But composite and stiff materials can warp less than semi-rigid polymers. Elastomers tend not to warp because they're elastic. And so if you get elastomers adhered well to the build plate, elastomers tend not to warp, but it's polymers like nylon, polymers like polypropylene, polymers like PLA, polymers like ABS, sort of these rigid plastics tend to see a lot of warping in this type of thermal processing. But when you go to a composite, they don't tend to warp as much. And that's really interesting. We'll see that at large scale in a couple slides because they've investigated this with big area additive manufacturing and had the same observation. So this is from my group. Either Locke or Kenny printed this, I think, or helped print these. But this border around here, these are polypropylene. These are tensile bars, so you'd do tensile measurements. These are dog bones for tensile bars to test the strength of the print. And you can see this film around the outside of the tensile bar, and this is called a skirt, for helping adhesion to the build plate. So this first layer, or the first couple layers, is printed with much higher surface area to help hold down the rest of the print. And so if you're into hobbyist 3D printing, you know that people use glue sticks or the right type of tape or hairspray or some sort of acetone solution of PLA to hold down their prints and make the print bed sticky. And one way you can increase the adhesion force is to increase the area of the print. And so this skirt helps to glue down the print on the bed. So we won't go into all the techniques. They're detailed in some of the online guides, but this is some of the strategies that you might want to be aware of if you're having this warpage problem in conventional material extrusion AM. And some of these tools are built in to the printer design software. And so you'll see lots of these types of structures if you get deep into 3D printing, lots of different shapes. Any questions or comments on that? All right, so like I said, if anyone's ever done any hobbyist printing, especially if they've tried to print these blocks like this or objects with a lot of material on it, this warping is pretty common, but it can be combated through a number of different strategies. Now, if we go back to SLS and we talk about what warpage can happen there, there's some online guides for that. But since SLS has been industrialized, at least for a few different materials, there's a lot of good scientific information out there in terms of studying the effect of warpage, studying the densification, and also studying the defects that occur when you do SLS. And so we'll talk about SLS for the next few slides. So warpage can occur from these built-in stresses or this differential temperature, as we discussed in material extrusion AM, where the temperature is really cycling in the part. And you see here that the temperature transients are on the order of tens of seconds, or in some cases, 100 seconds. So if you look at this temperature transient, that's right about at 1,000 seconds, and it goes maybe a little bit past 100 seconds. And so that's a long time temperature transient, because material extrusion AM is a relatively slow process. And so this thermocouple location is heated up, and it takes a while for that heat to dissipate. In SLS, we have a much different situation because the laser is moving rapidly. And in general, the bed temperature is pretty high above TG, but below TM for this material. And so the thermal transients are short in SLS. And we looked at some of the thermal transients in the SLS unit, where the temperature was cooling within tens or hundreds of milliseconds. And so that's a much different time scale of thermal transient than we saw at the beginning of this lecture. But what can change significantly is this idea of the density or the apparent density of the part as we change the energy density that's put on the powder. So remember, we're fusing powder together. And so if we just fuse it a little bit, we get a little bit of coalescence, but there's still a lot of gaps in the powder. And so we can have a low apparent density from that. And if we go to higher energy, if we put more energy into the powder, we can get more and more densification, and we get a higher apparent density, of course, up to the bulk density of the pure polymer, which is going to be on the order of about 1,000 kilograms per meter cubed, or about 1 gram per centimeter cubed. For polyolefins, a little less. Nylons is about 1. So this is close to full sintering or full densification, as we might call it. And depending on the orientation of the part, it changes a little bit. But this densification, you can imagine if you're densifying, let's say, well, this is not a perfect example, but say we're densifying a tensile bar on the surface of this bed, and we densify this part of the tensile bar a lot, and don't densify this part of the tensile bar as much. Now you have a porosity gradient, or you have a density gradient, and that can cause curling, and that can cause built-in stresses in the part. And so as soon as this tensile bar starts to curl off of the bed, then you can get the part running into the roller here. Here's the roller. And we saw an example in the SLS section about parts sliding around a little bit in the powder bed because they were getting hit by the roller because of curling and because of poor powder spreading. So the mechanism of how you get warpage in SLS is a little bit different, and it's due to this densification, but we still need to pay attention to it because it can cause print defects and print failures. And so what happens as you change this energy density as well, in a full build, you can start to get a deviation between the desired thickness and the actual part thickness, depending on what your densification is. Because of course, if you densify more polymer in there, the layers can be a little bit more thicker. You get some sinkage of the part into the bed, and you spread more powder on that area. So this is not the thickness of one layer. I can't remember exactly how many layers that took them to get a 3 millimeter part thickness, but if you densify further and further and further, you'll tend to get a thicker part because you get more coalescence and more powder in that area. And so you see that this can cause significant deviations when you're trying to densify the part fully. And so this needs to be corrected for in the software. And so even though you plan a 3 millimeter part, it doesn't necessarily mean you'll get a 3 millimeter part depending on how the printer parameters are put together. And I had a discussion today in office hours about using geometric feedback of real parts to do replanning of the CAD model. And so you have a desired CAD model, you print it on a certain printer, you scan that real printed model, and then compare that three-dimensional real object that now you have a digital scan of to your CAD plans, and then the computer can start to figure out where the dimensions of the CAD model need to be tweaked in order to get the desired part tolerances. So we won't cover that very much in this class, but that's out there, this sort of idea of real feedback and how to get tweaked or optimized CAD models for printing condition is something that's coming, and is something that different companies are trying to implement in their software. But anyway, this can happen depending in SLS, depending on the energy density of the build. And what happens as a consequence of this is you can get significant warpage. So if you're printing these cantilevers, because it's really easy to look at warpage, so you would be printed, at least in this one, well, this is either 0 or 90. I'm not exactly sure which orientation. I'd have to read the paper again, but I think it's printed in slices like this. You can measure the warpage as a function of the preheat temperature. And of course, as you preheat to higher temperature, you get to lower and lower warpage. So hotter polymers that are held closer to the processing temperature, because this is polyamide. Well, this is a PA2200 HDPE composite. So it's a mixture of polyamide or nylon, and high density polyethylene, that's going to be processed at 180, 190 degrees Celsius. And so if your preheat temperature, your bed temperature is close to the processing temperature, like up here, you'll get less warpage. And so in SLS, you can start to optimize the densification parameters and the bed temperature in order to combat warpage of these parts. Any questions so far? All right. So this is a really interesting study right here, and they talk about how to correct some of these defects. And so there's a computer algorithm that they use, and we won't talk about the algorithm, but depending on what the defect is, whether it's going to be a curling defect or whether it's a shrinkage defect or whether it's a geometric defect on the corner due to the type of printing they're doing, this is talking about controlling or adapting the geometry of the object to get it to print to the desired size, or to get it to print to the desired accuracy. So this is a sort of emerging technique where you change CAD model to get desired shape, knowing that there are print deviations. So this is a little bit hard to explain since we're not going to go in depth in software, but it's, let's say, a calibration of the printer, and it's a geometric calibration. So say that you know the speedometer in your car reads fast, say if you're traveling 60 miles an hour actually, and your car speedometer is reading 65 miles an hour, you know that there's a calibration error in your car speedometer. And so you can calibrate in your head, okay, if I'm driving 65 as indicated on the car, I know that I'm really going 60 miles an hour, which is what the police will read on their radar gun. Same with this. These are, in essence, geometric calibration errors in terms of how the print is done. And the software can be calibrated for these errors. And so again, the CAD model or the print planning model can be tweaked in order to account for these errors. And there's various automatic ways to do this. This is sort of the forefront of 3D printing software, not just how to control the printer based on the shape that's in the CAD model, but how should you control the printer to actually get the desired shape that you want ultimately. So for people interested in software and people interested in optimization of geometry, you can read this. It's really interesting. And like I said, that software is just emerging in a lot of the printer control or in the CAD planning software that people are starting to use. Okay. Yeah, so this is just a table showing what they call pre-compensation. So if you're going to have curling defects or shrinkage defects or a trapezoid defect, they come up with a calibration for what the compensation should be. And so if they don't apply the calibration, they get a deviation. If they do apply the calibration, they still get a deviation because nothing's perfect. But you notice that in general, the compensated deviations are less than what the uncompensated deviations are. So again, if you're interested in this sort of geometric correction in the model to begin with, rather than trying to correct for defects as you're printing, this is, you can check out this paper. And there are lots of other papers emerging on this. any questions so far? Any comments, things people want to talk about? All right. So this is a little bit routine, but oftentimes you can get just stringing defects or other defects in terms of how the polymer is flowing out of the nozzle. And so this is just something that you might want to be aware of if your structures are looking ugly, like this one right here. This is just a way to combat this. And so, like I said, there's a lot of online guides as to how to do this for material extrusion AM. And so this idea of retraction steps or picking the head up or tweaking the temperature can be ways that you can help fix some of these defects. And so you can see online guides for that. Print speed is also a way. So we're back to material extrude, just a couple slides on material extrusion AM. Because of the long time transients in material extrusion AM like this, the print speed can have a big effect in terms of the defects that you can get. So they talk about travel speeds. So travel speeds is the speed at which the printer moves while not printing, and then a print speed is the speed at which the heated liquefier moves when it is extruding polymer. And so this gives you some ideas, some qualitative ideas as to how to optimize this type of printing. Oh, I don't know why we went back and forth between material extrusion AM and SLS. But anyway, sorry for the out of order slides. But under extrusion is interesting. We talked a little bit about under extrusion and over extrusion when we were talking about gauged filaments. And so this can also occur due to deviation in filament diameter. But if you start seeing some parts that look like this, where you can distinctly see gaps, that's a key indication of under extrusion. And so there are some various ways to try and mitigate this, including making sure that you have an exact diameter of the filament. So in industrial material extrusion AM, it's really important to get a well-gauged filament or very consistent diameters, because the machine isn't measuring the flow rate of the material coming out of the heated liquefier. It's only measuring the length of filament that it's putting into the heated liquefier based on how much extrusion it needs. So it doesn't necessarily know how much polymer is in the heated liquefier. It just knows the length of filament that it's putting in. So if the filament diameter is too small, it's putting in too little polymer and you get under extrusion. Or if the filament diameter is too big, then what you put in print planning software, then you get over extrusion, and that's not good either. So these are some of the common defects that you might encounter when doing material extrusion AM in this case, or SLS as we talked about previously. Now, one of the ways that people have tried to change the defect density or the print quality by dealing with the material rather than dealing with the machine settings is to look at this issue of bimodal blends. And for those of you that read a paper on this, this is really interesting in terms of they were talking about using bimodal blends of polymers to do road adhesion and to increase interfacial adhesion between roads. And so that was in, I think it was homework number 3. But these bimodal blends can also be used to improve the viscosity and improve the print quality of the material and also increase road adhesion. And so if you're not familiar with what molecular weight distribution is, you have something like number. And so we've talked about polymers that are, say, 10,000 grams per mole, 50,000 grams per mole, 100,000. And molecular weight distribution basically characterizes the breadth of the different populations of molecular weight in a sample of polymer. So this is also called the dispersity. And in old language, sometimes you see the polydispersity index, although we tend to call it dispersity now. But this molecular weight distribution is really important if you are interested in the fundamental polymer science in terms of viscosity, flow properties, things like that. And a bimodal molecular weight distribution, or a bimodal blend of molecular weights, is basically you take one molecular weight and another molecular weight, and you blend different molecular weights to change the dispersity. And of course, bimodal is just you have two peaks somewhere. And of course, they don't have to be symmetric like I've written here. Let me see if I can just erase that and put something else in. So this is a trick that's used often in injection molding. This is how different grades of polymers are made. So sometimes they vary the molecular weight, but oftentimes they'll vary the dispersity, or they'll mix different molecular weights together to vary the dispersity artificially. And so that works in 3D printing as well. And so this is an important tool that people are starting to look at for how to create new grades of additive manufacturing polymers that haven't been useful for injection molding or other types of polymer processing, but may become very important for material extrusion AM or SLS, the two thermal types of additive processes. So the reason why this works, we can talk about the polymer science and about why MW, or the weight average molecular weight, tends to control the viscosity versus a number average molecular weight. But we don't need to go into the details unless people start asking questions. Of course, you could take a polymer physics course or a polymer science course to learn about that. But this idea of tweaking the polymer flow properties through changing the molecular weight or changing the molecular weight distribution is a powerful technique to start to optimize the material for additive, rather than always worrying about optimizing the machine settings or optimizing the printing process. And of course, this can really help with defects. And so you can see from the different samples here. So neat is just, well, let me get back to my black pen here. So neat is just the base material. And then you start to look at the different bimodal blends. You can start to see different defects in terms of your road adhesion. And we know that that's going to lead to different mechanical properties. And so this is a really cool table from this paper where they talk about the void fraction for different blends, and they've got longitudinal and transverse tensile bars. So they're looking at the anisotropy. What they do is they measure the maximum tensile stress, but they correct it for the void fraction. So if you look right here, So for a void fraction of 0, the measured tensile stress, or the stress at break, is the same for the corrected. But if you have a voided sample, say something with 10.3% voids, you actually increase the corrected maximum tensile stress from 40.96 to 45.19. Maybe there's 1 or 2 extra significant digits in those numbers. You can just ignore that. But now this corrected maximum tensile stress is corrected for void defects. And in a perfect world, this is nearly all the same materials, so it should all be the same. But now you look at road adhesion and intrinsic anisotropy effects. Because we know when we do 3D printing, there's always this geometric factor. So there's always potentially some kind of anisotropy, or in this case, if we're doing material extrusion AM, there's always going to be these defects. We know they're there, but we really want to get an idea of the intrinsic material properties as well. So in the real world, let me go back to red before I forget that. So in the real world, of course, what matters is this number. So you make a part, you're going to get the stress to break, and that's the real number. So that's what your component needs to experience. However, if you're interested in studying the material, this void fraction is basically a geometric correction. Or you're correcting for the known defects so you can get an idea of what the intrinsic material properties are. Same with measured modulus, although this is an awfully formatted table, but you can sort of sort out what numbers go with what headings. And the corrected modulus, taking into account or correcting for void fraction. So you really can't design your part based on the corrected modulus, because you're always going to have these voids. You know, if you make this part by FDM, you're just going to have to deal with those voids, and that's going to have to be part of your calculation for the intrinsic material properties. But if you want to study what's going on with the material and not what's going on with the void, so you're decoupling material and geometric factors, looking at this corrected modulus is a first order easy way to do it. And you can still see effects from the blends and anisotropy effects as well. Any questions on this? Okay, so that's just some things I was thinking about for thermal stresses based on a couple of the conversations I had, but that was a quick rundown of some things that you have to worry about in material extrusion AM and in SLS, and then this paper on molecular weight distribution and corrected geometries is really interesting. Now in the box folder, we can go to lecture 10. You can find it here, so you can open up those slides, and of course my drawings will sync to box here sooner or later. And we're going to talk a little bit about defects, and we're going to talk about how defects in interlayer adhesion really are observed in 3D printed parts, how defects are automatically observed, and then maybe what defects occur in these different printing technologies. And so this is a general overview of how defects manifest in material extrusion AM or in SLS, or we'll talk about some defects in SLA. So SLA really didn't feature in cyclic thermal stresses because there's really no cyclic thermal stress to consider in that process. However, there's other types of defects that don't have to do with cyclic thermal stresses. So one of the things that we have to remember, we'll go all the way back to this diagram, is that semicrystalline polymers are more dense than amorphous polymers. And so this is a diagram of an amorphous. So if we're processing a semicrystalline polymer, the crystallization process itself can cause densification issues, and that can cause defects as well. So that's just something to remember if we try and connect what we're talking about now all the way back to the very first day that we started talking about polymers at the beginning of the semester. We have to remember this. So not only is the coefficient of thermal expansion of a given material important, the crystallization behavior and what parts of the part are semicrystalline or more crystalline than others, which depends on thermal history, might be important. And so, of course, we have to remember this as well. So we have a couple of different thermal transitions. We have TG, we have TC, and we have TM. Those all occur at different temperatures. So you can imagine as we're doing FDM, where you can think about on this temperature scale here, as we're crossing these different thermal transitions or getting near these thermal transitions, remember polymers are really cool because they can crystallize at different temperatures between TG and TM. And so TC can vary significantly depending on thermal conditions. TM can also vary. So let's say TC and TM can vary depending on the thermal conditions. And so if you've taken a polymer science class, you know that TC and TM can be anywhere between TG and TM0, which is the equilibrium melting point. And so depending on how long a material is allowed to crystallize, how thick the crystal is, the crystalline lamellae are, that will determine TC and TM. So that's sort of in the weeds of polymer physics, but this idea that you can have different crystallization in different places in the part is totally reasonable because of the long thermal transients that we saw in the previous lecture. And so this idea that the rate of crystallization changes between TG and let's call this TM0, which is TM0 is the thermodynamic TM at 100% crystallinity. And of course, we never have a polymer that's 100% crystalline. And so TM0 is a theoretical number, but TM oftentimes is not too far away from TM0. But at any rate, the rate of crystallization is slow near TG because molecules are starting to move slowly near TG. So the rate of crystallization goes down because at TG, remember, you had the rubbery to glassy transition. And so you can imagine that for a polymer to crystallize, so the polymer chain or polymer chains need to move a lot to crystallize, right? And that takes time. And so you've seen some of the YouTube videos of super cooled water in a water bottle. So you have a water bottle that's really cold. It's been in the freezer for a long time, and you open the cap and the whole bottle crystallizes at once very quickly. So that kinetics of water crystallization is fast because that's a small molecule. And so small molecules crystallize quickly. As soon as you cool iron down below its melting point, it crystallizes rather rapidly. I mean, crystallization kinetics are known for many, many different materials, and they're rather fast for small molecules or metals. For polymers, crystallization can take a long time. Crystallization can take minutes or hours or even days. And so because polymers are these long chain molecules, it takes a long time for crystallization to happen. And crystallization gets especially slow near TG. Crystallization also gets slow at high temperatures near TM because of the surface energy difference between the melt and the crystal. That's sort of in the weeds again of polymer science. You don't need to worry too much about that. But near the melting point, the polymer doesn't mind if it melts or crystallizes very quickly. And so you tend to have lower crystallization rates at high temperatures because, of course, the crystallization rate is zero at TM0 because nothing's going to crystallize at the melting point in polymers. And so the rate has to trend towards zero at high temperatures. But right in the middle, this is actually usually about halfway between TG and TM0, you have the maximum crystallization rate. But now, if you're processing at all these different temperatures, or you have these cyclic thermal stresses, the kinetics of crystallization or the rate of crystallization can be different depending on the thermal history of your part. This leads to different crystallinities in different places. It can also lead to different mechanical properties in different places of your part, because we have to remember that things tend to have higher strength when they're more semicrystalline. So all these things add up for internal stresses and defects. And so getting an idea or getting a quantitative model of what's crystallizing where, depending on the thermal history, is really, really complicated. And this is something that people are continuing to work on in order to be able to model how these stresses are built up in the printer and how printer control software might be used to combat some of these thermal stresses. And so the other really interesting thing in this area is if you post process by thermal annealing, and you can check out these links right here. So if you say print something and it comes off the bed amorphous, and then you thermally anneal it and you get some crystallinity in that sample, you can see that the heat resistance and the impact strength goes up depending on what type of filaments you have. So by taking a printed part and then treating it or heat treating it at a certain temperature. If you're familiar with metals, you know they heat treat metals all the time to get the right grain structure and to relieve thermal stresses and things like that. We can do very similar things with polymers where the crystallization physics and the semi-crystallinity of the part are different. And we're not going to talk too much about grain structure in polymers because it's a much different ballgame than grain structure in other materials. But this post-processing annealings helps to smooth out a lot of the built-in stresses and built-in anisotropy in the parts as they come out of the print, uh, out of the printing process. So that's a lot of material. I'm going to give some examples of this in a sec, but I want to pause here and just ask if there are any questions or comments or if people have seen these defects before. I know some people have worked on this, at least in my lab, but I'd be happy to chat about this or answer any questions while we pause here for a second. All right, so there's literature on this. If you're interested in pursuing something like this for your paper, there's really interesting studies of defects or warpage or these other material effects. Of course, what this paper shows is that annealing only works for some types of polymers and not others. And so that's interesting if you want to pursue that further. So this is a comment, and we're not going to watch these videos, but this is a comment that you can start to anneal PLA to above its glass transition temperature, and of course below its TM, so PLA is semi-crystalline. You can get you can increase the mechanical properties of PLA. So you're basically annealing to form more crystals. You increase the rate of crystallization, and you get better looking parts. And you can check out these YouTube videos. I think they were done by some folks in the hobbyist community. So it's really interesting how they do experiments and then test this in some of their shops. So I suggest you check this out. Now, defects and this idea of cyclic thermal stresses are really interesting because as you start to print big stuff like this, of course, if you're printing a little MakerBot robot or something like that, yeah, you'd like to get good prints. But if you're industrializing 3D printing and all of a sudden you start to get failures in a large print like this, that can become an issue. And so you can see a couple of the defects in this print. So you can see some waviness in the car. You can see some big lines. Eventually, I'll show you something that's delaminating in a couple slides. And so it took a while to get to something that at least looks this good for this 3D printed car. And we'll talk about how the folks at Oak Ridge were able to accomplish this. So again, as you're printing big stuff, there can be big defects, and so you can get geometric defects. You see some problems here with this sort of overhang. You see issues here where they're not getting perfect extrusion, and so it's really hard to go back and fix those or really hard to correct those on the fly. So you'd like to have a well-tuned process where you don't have to deal with this and you're throwing away hundreds of pounds of composite plastic. So this is a really interesting article. I suggest you read it. And so when they test printed this car at Oak Ridge, so this is not at the auto show, but they were practicing for the auto show. And at first they were going very slow because they wanted to make it perfect. They wanted to get good shape resolution. And so they were printing it slow, and they got this massive delamination. So slow printing led to massive delamination. That's really interesting. So this was the car they printed before they printed this one. And so showing up with something like this at the auto show would not be great. And so what they discovered is that they were getting delamination due to differential cooling, because in BAM, or big area additive manufacturing, and we've looked at those machines before, there's no oven to keep part warm. So you'd really like to have an enclosed chamber, just like we saw in some of the industrial FDM, to keep the part warm and to decrease those thermal stresses. But because BAM is done basically in an open environment, just with some shields around it for protection like this, they were seeing massive delamination. And so what they did was that they started to print the car faster to keep the car hotter in order to decrease the built up stresses. So they found that when they let the part cool too much and then went back over it or went to a different part of the car, you can see this gradient structure here. So you're putting a different amount of heat as you start to build up these layers. You see this peeled right up due to the cooling and the differential thermal stress. Same with some of the fenders. So you're just getting massive delamination because the layers were too cold, and so you weren't getting good adhesion to resist the delamination, and you were getting this differential shrinkage, which caused the thermal stress and the peeling or the delamination. So as you printed faster, you kept the whole car warmer, and you were able to get a better result from keeping the whole print hotter to resist these thermal stresses before you got good interlayer adhesion and the whole car would stick together. Another critical thing that they talked about in one of the Oak Ridge reports, and we saw this exactly in the marked forged onyx material, was that ABS has warpage, but carbon fiber ABS and I think this is 10 or 20% carbon fiber in ABS, doesn't have any warpage or has minimal warpage based on the flatness of these bars. And so building this car out of a composite material, because the composite is stiffer, even though it's harder to extrude, takes more energy, is slower to extrude, you get less warpage if you can combat the thermal stresses that you saw in the car. So that's an interesting result. And a lot of composite filaments, of course, will be used in industrialized AM. And so this is an advantage of using stiffer materials. The disadvantage of some of these composites is shown in this study right here. And here's a PDF if you want to check it out. And so as they're trying to figure out what the mechanical properties of big area additively manufactured parts are, they did tensile bar printing, or they printed plates and then they milled tensile bars at different orientations. They dried them according to ASTM protocol, and then they tensile tested them in this humongous tensile tester, which is pretty awesome. I'm sure these bars were nice and loud when they broke. But this is an interesting study now, because even though they got less warpage with the carbon fiber composite, when they went to look at the strengths, so they have ABS in different print orientation. So the ABS is the white stuff right here that's unfilled, and here's the print orientations defined right here. And these were milled tensile bars, but you could think about printing the tensile bars in the orientation like I showed you in the previous slides. You could, on a desktop printer, you can just print the tensile bar shape. There are some caveats, but it's reasonable. And so all of the printed material in ABS basically met what the spec was for the modulus. So the spec of the ABS was about 2.25 gigapascals in terms of what the modulus was. And so no matter how the print orientation went for the ABS, they got very reasonable results. And so this is nice. It's predictable. You can figure out how to design a part based on limited anisotropy of this material and based on it approximating what the spec is, no matter what the orientation is. Carbon fiber ABS, the spec is a lot higher. This is 13% carbon fiber. I knew it was between 10 and 20%, but this is 13% carbon fiber ABS. The spec is 7.7 gigapascals, so a lot stiffer, but only the 0, print orientation met the spec. So this is 0, 0, in case you can't see all these little lines. This is 90, 90, and then this is 145, 135. So the 0, 0 spec, of course, is 2 layers. There's a degree for each layer. So these are 2 layers on top of each other, and the roads are oriented in the direction of the mechanical test. So you're going to pull these tensile bars from the top and the bottom here. And so as long as you have the road orientation in the direction that you're performing the tensile test, you're all good. The carbon fiber ABS meets spec, and so the printed part is reasonable. There's issues with the 90-90 and 45-135, and what you notice is now you're pulling across roads, and so you're pulling tensile bars across road adhesion interfaces. And that's causing real issues because you're not even coming close to spec with those materials. And this shows that there's real road adhesion issues in the composite. So this is showing some of the advantages and the disadvantages of neat polymers, where you get really good road adhesion between the layers because, of course, this is all polymer. You can melt it. You can get good bonding of the roads together depending on the conditions, whereas the carbon fiber ABS looks pretty good for warpage, but this data indicates that there's real road adhesion issues when you start to pull across roads. Because, of course, if you have a lot of carbon fiber in there, the carbon fiber doesn't do anything to fuse the roads together because it's basically a place where polymers can't diffuse. And you know that putting fillers into polymers also increases polymer viscosity. And so if you're increasing polymer viscosity, it's going to take a longer time in order to get those roads to adhere. And so there's lots of issues with trying to process composites and trying to, in essence, diffuse these composites together at the interface. And you can see that in the Young's modulus with it not meeting, with the material not even close to meeting spec because of the road adhesion issues. Any questions on this so far? Okay, I think we'll go till 6:45. That'll be an hour and 15 minutes of class, so you'll get your money's worth. And so we'll just have a few more slides and we'll have a regular length lecture because we have a few more things to talk about. So what they observed with these dog bones, so when you do the post-test analysis, they were breaking the 0, 0 dog bones sort of all right in a predictable way. So all the roads failed at some sort of stress concentrator, but they all failed in reasonable ways. For the 9090 and 145, 135, they got a lot of this fracture between layers. And so this is row or layers on top of one another failed at different locations. So rather than breaking straight across like the 00 samples did, the 9090 samples look okay, although there's some roughness there. You can really see it in the 3545 that this the splitting along the interface and this sudden brittle failure was a big issue in terms of not getting the predicted properties. And so finally on strength, the ABS is a little bit low on spec, but not too bad for ultimate tensile strength. So this is, about 80% of the ultimate tensile strength of the ABS. And so that's not too bad for an additively manufactured part. And you saw major issues in the carbon fiber ABS, not even coming close to meeting spec because of these road and layer adhesion problems. So as you start to think about how do you design, let's go all the way back. How do you design a 3D printed component that looks like this 3D printed car? You have to pick the right material to try and decrease the warpage, but you need to have the right processing conditions and you need to be able to have the right thermal history of the part in order to decrease these built-in stresses. Then, of course, as you use the component, you need to be able to take into account the anisotropy of the material, depending on what the orientation of the print is, what time there is between print layers, what sort of interlayer or road adhesion you might experience. And so all of these things have to be assessed because we don't have a comprehensive model for this yet. So it would be nice to say, well, if you just print like this, it will work in every single FDM model or material extrusion AM model. It'll work in all the printers, but that's not really reality because each print is a little bit different and because we don't have a good thermal model for all the different types of printing, it's very difficult to predict. And we'll talk a little bit about modeling and what people have done, but this usually needs to be calibrated and these observations need to be made for different materials, different builds, and different machines. So I think that's all we'll cover tonight. We have a few more things to talk about and then we'll keep going. Are there any questions from the class, any comments that people want to make before we sign off for the evening?
So the specs that you were talking about for, I think, slide 13 and 15,
yep.
The specs aren't based off of additive manufactured parts, right?
So that's a very good question. And so sometimes suppliers will give you a spec based on an injection molded part. Sometimes if you buy a filament, they'll give you a spec and that will actually be based on a 3D printed part in a specific orientation. And so I think in this spec, because their ultimate tensile strengths in general are a lot lower than the spec, this is probably an injection molding spec because they have the intrinsic porosity and the intrinsic defects in additive. And so because it's systematically lower, I think this is an injection molding spec for that material. But it's worthwhile to ask the manufacturers, how was the specification measured, under what conditions, what processing did you use to develop this spec? Because sometimes when you just open MATWeb, or if you open the book of polymer material properties, it'll be for a machined injection molded bar, or it'll be for a cast rod or something like that. Or if you buy a reel of filament, say from a 3D printing company like Stratasys, they'll give you the spec for a 3D printed material. Then it's up to them to tell you how they printed it, what orientation. Sometimes even additive manufacturing companies will publish what the anisotropy is. So they'll publish different specs depending on the print orientation. And so there is no universal spec other than assuming it's from injection molding, because of course that is, injection molding is usually the industry that all these polymer feedstocks are used for. But it's worthwhile asking questions about where that spec comes from and how it was developed. So that's a good question.
Thanks.
Any other questions? Okay, like I said, we'll keep going on this for a couple more lectures. I have a few things I want to circle back and fill in. And so again, if you're interested in a specific topic, let me know. Otherwise, work on your homework this weekend and shoot me any questions you have, and I will see you on Zoom on Tuesday. Thank you very much.
Thank you.
Thank you.